Hi, my name is Tjachyadi, and I currently teach at W.T. White High School in Dallas, Texas. Today, I would like to discuss reversible reactions, chemical equilibrium, and Le Chatelier's principle, aka how to make as much stuff as you want. Now, let's use the following reaction as an example. When nitrogen gas and hydrogen gas are combined in a container, ammonia gas is produced. This is called the forward reaction. However, ammonia gas can also split back into nitrogen gas and hydrogen gas. And this is called the reverse reaction. This is an example of a reversible reaction. A reversible reaction is a reaction that does not go to completion and occur in both the forward and reverse directions. When the forward reaction and reverse reaction happen at the same rate, the system is in a chemical equilibrium. When a chemical equilibrium is achieved, the concentration of reactants and products stays constant. The goal chemists always strive to achieve is to maximize the amount of products while minimizing the amount of excess reactants. Chemical equilibrium causes some challenges for chemists because there will be some reactants not converted to products. In other words, chemical equilibrium leads to inefficient use of resources. The solution for this predicament is the Le Chatelier principle. According to Le Chatelier, if a stress is applied to a system at equilibrium, the system shifts in the direction that relieves the stress. Stress is any kind of change that upsets the equilibrium, such as adding or removing reactants or products, or even adding or removing heat. Now, I am going to demonstrate how stress affects the chemical equilibrium. For the following demonstration, you need to know that R is for reactants, P is for products, pushing is for adding reactants or products, and pulling is for removing reactants or products. I am a reaction in equilibrium. Pay attention to the R and P on my palms. Now, different types of stress will be applied to my equilibrium. When reactants are added to the system, the equilibrium will shift to the right. When reactants are removed from the system, the equilibrium will shift to the left. When products are added to the system, the equilibrium will shift to the left. When products are removed from the system, the equilibrium will shift to the right. This table summarizes the different types of stress applied to the system and the effects they have on the chemical equilibrium as shown in the demonstration. So the solution to efficiently use all the reactants and to produce maximum amount of products is either continuously adding more reactants to the system or continuously removing product from the system. Now, a chemistry example. Pay attention to the following reaction. The color of the reactant is pink, and the color of the product is blue. In this reaction, heat is considered as a reactant. The solution showed in the video clip has both reactants and products in equilibrium, and both exist in a significant amount. Thus, the color of the solution is violet. When the heat is added to the system, equilibrium is shifting to the right, changing the solution color to blue. And when the heat is removed from the system, equilibrium is shifting to the left, changing the solution color to pink.